Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. In the earlier video, we did inductive effect and electromeric effect. Today, we'll be doing resonance or mesomeric effect. So, if a compound having a certain molecular formula, for example, benzene, can be represented by different structural formulae which differ only in the arrangement of electrons and not of the atoms, then such like structures are called resonating structures or contributing structures or canonical structures. And the compound as a whole cannot be represented by any of these structures but as an average or hybrid of these structures, which is known as resonance hybrid. This resonance hybrid has the characteristics of all the contributing structures. This phenomena is known as resonance or mesomerism, and the various resonating structures represented by a double-headed arrow of benzene. These are resonating structures of benzene, and this is the resonance hybrid for benzene. As the pi electron cloud is distributed over a greater area, the charge density decreases, the energy of the hybrid decreases, and stability increases. So resonance hybrid is more stable than any of the resonating structure. Similarly, resonance in carbon dioxide. The structural formula of carbon dioxide, according to Lewis concept, is each carbon is having double bond with oxygen atoms. So the bond length should be 122 picometer, but actual bond length is 115 picometer as determined by the spectrochemical studies. So this can be explained from the various contributing structures for carbon dioxide. In this structure, there are two double bonds, a single bond and a triple bond here, and a triple bond and a single bond here, and the actual bond length will be average of all the three double, single and triple bond lengths. In monocarboxylic acids. Monocarboxylic acids are the organic acids, and their acidic character or proton releasing tendency is explained on the basis of resonance. This oxygen, because of resonance, the electrons from the oxygen move towards this doubly bonded oxygen. As a result, there is a partial positive charge on oxygen which attracts these electrons towards itself, making the release of proton easier. So these electrons move towards this side and proton is released. So carboxylic acid acts as a acid. Then resonance energy. The difference in internal energies of most stable contributing structures for a particular compound and its resonance hybrid is known as resonance energy. So this structure has lesser 150 kilojoules energy, lesser than either of these contributing structures. So it is more stable by 150 kilojoules. So 150 kilojoules is the resonance energy for benzene. Conditions for resonance. The resonating or contributing structures must differ only in the position of electron pairs and not of the atomic nuclei. The atoms remain in their position, only the electrons move from this position to this position. Then resonating structures must have the same or nearly the same energies. All the resonating structures may not contribute equally to the hybrid. Equivalent structures contribute more as compared with non-equivalent structures. For example, for benzene, the Kekule structures are equivalent, so they contribute 72% to the resonance hybrid, whereas the Dewar structures given by Dewar are not equivalent and contribute only 28% to the resonance hybrid. Charged structures have less contribution towards the hybrid in comparison to uncharged structure. We will see this in carbon dioxide and acetic acid. The contributing structures with more covalent bonds contribute more towards the hybrid than the structures with less number of covalent bonds. For example, the structure 1 for buta 1,3-diene has a pi bond extra, whereas it's resonating one pi bond less. So this structure will be contributing more because it has more bonds. The structure 1 has greater contribution because of number of covalent bonds being more. There is an additional pi bond. The contributing structures in which negative charge is present on more electronegative atom and positive charge on less electronegative atom will be giving greater contribution to resonance hybrid. So out of these structures, this structure having negative charge on electronegative oxygen atom will contribute more than this which is having positive charge on electronegative oxygen atom. And out of the 3 atoms, this will give the maximum contribution because it does not carry any charge. That contributed structure contributes more towards the hybrid in which all the carbon atoms present have a complete octet. So this carbon has complete octet. It will contribute more towards hybrid than this which is having only 6 electrons. It will give less contribution. It has an incomplete octet. So this was about resonance. Now resonance effect or mesomeric effect. We have seen that resonance or mesomerism involves movement or flow of electrons in conjugated systems, that is having sigma and pi bonds in alternate positions. This leads to centers of low and high electron density resulting in positive and negative charges respectively. The phenomena of movement of electrons is termed as resonance effect or mesomeric effect. It is of 2 types, plus R or plus M effect. A group is said to have plus R or plus M or positive mesomeric effect when the displacement of electron pair is away from it. This group will contribute towards the double bonded system. For example, OH, alkoxy group, amino group, secondary amino group and thioether group, they contribute the electrons towards the double bonded system. Double bond pulls the electron, lone pair of electrons towards itself. So as a result, a negative charge will come here when these electrons move here and a positive charge results on the atom. So this effect is plus R effect. Similarly, in amino also, when it is in conjugation with double bond, electrons move to this side. These electrons move here. Negative charge comes here and a positive charge. This is plus R or plus M effect. Whereas the minus R or minus M effect is observed when displacement of electrons pair is towards it. For example, oxygen being more electronegative pulls the electrons of double bonded system towards itself. So this is minus R effect. Similarly, in ester also, electrons move here and these electrons move towards the group. This is minus R effect. So resonance effect is also called conjugation effect because in these compounds a multiple bond is in conjugation with either a multiple bond or lone pair of electron. Applications of resonance effect. We can explain the acidic strength of phenol. So phenol will give a proton to form phenadiene. Now phenadiene we can prove from resonance is more stable than phenol. So thereby the reaction proceeds in forward direction and a proton is released, making the phenol acidic in nature. So this can be explained on the basis of resonance. Both phenol and phenadienes show resonance, but in case of phenol, the resonance that occurs, the doubly bonded electrons of the benzene ring will pull the electrons of lone pair of electrons of oxygen towards itself. So these electrons move here and electrons are repelled to the next carbon atom. In the next structure, the electrons move to the next bond and these electrons to this carbon atom. So as a result, a negative charge results here and a double bond is formed here. In the next structure, these pi electrons move to the next structure and these electrons to this structure. So a negative charge results here and a double bond results here. Then in the next structure, the electrons migrate to the next bond and the bonded electrons move back to the oxygen atom, resulting in this structure. So overall, the 5 structures can be represented by the resonance hybrid, where there's a partial positive charge on the oxygen atom and the negative charge moves on the benzene ring. In case of phenadiene, the negative charge resides on oxygen atom. These electrons are pulled by the conjugated electrons of the double bonds. So a double bond results here and electrons move to this atom, which in the consequent structures move to next carbon atoms. Thus the whole negative charge is dispersed on the benzene ring and a phenate ion is stabilized because of resonance. So when we compare the resonating structures of phenol and phenate ions, in the hybrid for phenol, the partial positive charge is on the electronegative oxygen atom, which makes its contribution less towards resonance hybrid, making it less stable than phenate ion, where there is no negative charge, no positive charge on the electronegative oxygen atom. Then secondly, there's charge differentiation in phenol ion, whereas there's no charge differentiation in phenate ion. Then thirdly, the negative charge of oxygen atom is distributed on the entire benzene ring in case of phenate ion, making it more stable. So as phenate ion is more stable than phenol, so reaction will proceed in the forward direction and phenol will give a proton and act as an acid. We can also use resonance effect to explain the acidic character of carboxylic acid. Again, the acidic character of carboxylic acid is due to release of proton. So carboxylic acid gives a proton to form carboxylate ion. While we study the resonating structures of both carboxylic acids and carboxylate ion, we again see that in carboxylic acid, there's a partial positive charge on electronegative oxygen atom, and also there is charge differentiation. Whereas in carboxylate ion, both the structures are equivalent structures, so they contribute more towards resonating hybrid, and also there's no partial positive charge on electronegative oxygen atom. So the hybrid of carboxylate ion is more stable than that of carboxylic acid. So carboxylic acid releases a proton to form a more stable carboxylate ion and acts as an acid. Now, distinction between resonance effect and inductive effect. Both resonance effect and inductive effect are permanent in nature, but they differ in many respects. The resonance effect occurs in conjugated systems, whereas inductive effects occurs in saturated system. Here, the transference of pi electron takes place, whereas it involves the transference of sigma electrons, inductive effect. It involves delocalization of electrons. It does not involve any delocalization of electrons. It does not undergo any change in charge density with distance, whereas the inductive effect decreases as we move away from the atom involved in the initial polar bond. So that's all in today's video. Thank you. Have a nice day. If you like the video, please do share and subscribe.